Hello everyone, welcome back to David IB Course. Today we're going to talk about something you think you know, but you probably don't. Gravity. We're going to uncover the weird truth about it, and why physicists, following one of the greatest minds ever, say it's not even a force. Now hold on, I don't know what you're thinking. In school, we all learned that gravity is a force. It's the classic apple falling on Newton's head story. But what if I told you that modern physics has a completely different, and frankly, much cooler explanation? Albert Einstein totally rewrote our understanding of the universe with his theory of general relativity. And by the end of this video, you'll see exactly what he meant. Let's rewind a bit. Back in the 1600s, the brilliant Sir Isaac Newton gave us his law of universal gravitation. It was revolutionary. He described gravity as a force of attraction between any two objects with mass. The Earth pulls on an apple, causing it to fall. But get this, the apple also pulls on the Earth, just with a much, much smaller effect. This idea worked incredibly well. Using Newton's equations, we could predict the orbits of planets, the rhythm of the tides, and the motion of the moon with stunning accuracy. For over 200 years, Newton's gravity was the undisputed law of the cosmos. But as perfect as it seemed, Newton's theory had a few nagging problems. Little cracks started to appear. For one, the orbit of the planet Mercury didn't quite match the predictions. It was off by just a tiny amount, but it was a persistent error that no one could explain. Another puzzle was light. Astronomers observed that starlight bent as it passed near the sun. The light is made of photons, which were thought to be massless. How could a force of attraction pull on something with no mass? Even Newton himself was bothered by his own theory. He couldn't explain how this force of gravity could act instantly across vast, empty distances. It was like spooky action at a distance. How did the sun tell the Earth to stay in orbit? Then, in 1915, a patent clerk turned physicist named Albert Einstein came along and changed everything. He published his theory of general relativity, and it completely turned physics on its head. Einstein's radical proposal was this: gravity is not a force at all. It is a consequence of the geometry of the universe. To understand this, let's use a famous analogy. Imagine the fabric of space and time, what we call spacetime, is like a giant, flat, stretchy trampoline. Now, if you place a heavy bowling ball representing our sun in the middle of that trampoline, what happens? The fabric sinks and curves around the ball. The bowling ball has warped the shape of the trampoline. Now roll a small marble, representing a planet like Earth nearby. The marble doesn't get pulled toward the bowling ball by some mysterious force. Instead, it simply follows the curved path created by the bowling ball's weight. It rolls around in a circle, trapped in the dip. That, in essence, is Einstein's idea of gravity. Massive objects don't create a force. They warp or curve the very fabric of spacetime around them. And other objects, big or small, simply move along the straightest possible path through this curved spacetime. So, when you drop your phone, it's not being pulled down by an invisible tether to the center of the Earth. Instead, the massive Earth has bent spacetime all around it. Your phone is simply following the most direct path available to it through this curved landscape. What we perceive as the force of gravity is actually just the feeling of moving through this warped geometry. This new idea beautifully solved the old problems. What about light bending around the sun? Well, since light travels through spacetime, it too must follow the curves. It doesn't need mass to be affected. It's like a tiny ant walking across the curved trampoline. It has to follow the shape of the fabric. This exact effect was triumphantly proven during a solar eclipse in 1919. Scientists measured the light from distant stars, and it had bent by the exact amount Einstein's theory predicted as it passed the sun. It was a massive confirmation. And Mercury's weird orbit? General relativity predicted its path perfectly, right down to the last decimal. Let's take this to the extreme. What is a black hole? It's not a cosmic vacuum cleaner with an impossibly strong gravitational pull. According to Einstein, a black hole is a region where an immense amount of mass is crushed into such a tiny space that it bends spacetime to an incredible degree. The curve is so steep, so deep, that it creates a cosmic one-way street. Once you cross its boundary, the path forward only leads inward. The curvature is so extreme that nothing, not even light, the fastest thing in the universe, can travel fast enough to climb back out. So is gravity a force? In our everyday lives, thinking of it as a force works just fine. But at its deepest, most fundamental level, it's something far more elegant and profound. It's the shape of space itself, a silent, invisible architecture that governs the dance of planets, stars, and galaxies. It's not a pole, it's the path. And that is a truly mind-blowing thought. Thanks so much for watching. If you enjoyed this journey into the cosmos and want to explore more amazing ideas, please hit that like button, subscribe to David IB Course, share this video with anyone who loves to have their mind blown. See you in the next one. Presented by David IB Course.